All right, today we're cracking what I like to call the Carbonyl code. We're going to unlock the chemical secret behind, some of nature's most amazing scents, and on the flip side, some of industry's most heavy-duty chemicals.
So let me ask you something. What do you think the sweet smell of vanilla, that warm spice of cinnamon, and an industrial solvent like acetone all have in common? I mean, on the surface, it seems like absolutely nothing, right? But chemically, well, that's where they share a really cool secret.
And that secret? That's what we're calling the carbonyl connection. Think of it like a chemical signature that links all of them together. And you know what? It's been hiding in plain sight this whole time.
And here it is, the big reveal. The answer is this super simple but incredibly powerful little structure, the carbonyl group. All it is a carbon atom with a double bond to an oxygen atom. That's it. But this tiny little arrangement, it's one of the most important building blocks in all of organic chemistry. It's going to be the star of our show today, for sure.
Okay, so to get just a little technical for a second, chemists have a name for this. They call it a functional group. It's basically a specific part of a molecule that gives it predictable properties, how it's going to behave. And this carbonyl group, this C double bond O thing, that's the core component we're going to be digging into.
Now, what's so cool is just how versatile this one little group is. Seriously, think of it as the head of a massive chemical family. Depending on what else you stick onto that central carbon, you get completely different compounds. Today, we're focused on aldehydes and ketones, but this is also the parent of things like carboxylic acids, esters, amides. I mean, the list just goes on and on. It's like the ultimate chemical Lego brick.
So, let's zoom in on two of the most important members of this family. It's kind of like a tale of two positions, where one tiny little difference in structure creates two totally distinct families of compounds, the aldehydes and the ketones.
This really shows the key difference perfectly. Look, for an aldehyde, on the left, that main carbonyl carbon is bonded to at least one hydrogen. What does that do? It forces it to be at the very end of a carbon chain. We call that a terminal position. Now, for a ketone on the right, that same carbon is bonded to two other carbons. It's basically sandwiched right in the middle of the chain. And that's really it. End of the chain versus middle of the chain. That one little detail is the fundamental difference.
Okay, so we get what they are, structurally, but how do we, talk about them? Let's dive into the naming conventions. This is like learning the language that chemists use to keep track of literally millions of different compounds.
So when it comes to naming these things, there are basically two different systems you got to know about. First, you've got the common names. These are the old school names. A lot of them come from historical sources, like where they were first found in nature. Then you've got the IUPAC system. That's a big acronym. It stands for the International Union of Pure and Applied Chemistry. Just think of this as the official, rigorous, rule-based method that chemists all over the world agree on. Let's kick things off with the common names for aldehydes. A lot of times they get their names from the carboxylic acid they're related to. And you'll notice these Greek letters here, alpha, beta, gamma. That's just the old-fashioned way of showing where other groups are attached. The alpha carbon is always the one right next to the carbonyl group, and it goes from there.
The common names for ketones, they're even easier. You literally just look at the two groups attached to that main carbonyl carbon, list them in alphabetical order, and then just add the word ketone at the end. So the simplest one right here has two methyl groups. That would make it dimethyl ketone. But of course, everyone in the world knows it by its much more famous common name, acetone. Okay, so common names are fine. They're useful. But if you want a system that works for everything, you need rules. So let's dive in and master the IUPAC code. It's a really logical system, and once you get the hang of the pattern, you can name pretty much any aldehyde or ketone you ever see.
And the foundation of this system is actually beautifully simple. Here's what you do. First, find the longest carbon chain that has the carbonyl group in it. Then, you take the name of that parent alkane, like ethane or propane, you drop the final E, and then you just tack on al if it's an aldehyde, or -one if it's a ketone. So ethane becomes ethanol. Propane becomes propanone. See? Simple as that.
But what about for longer chains? Well, that's where we need to add some numbers. And the rules here are a little different for each. For aldehydes, it's super easy. Since that carbonyl group is always at the end of the chain, that carbon is always carbon number 1. No exceptions. For ketones, though, you have to start numbering from whichever end of the chain is closest to the carbonyl group. The goal is always to give that carbonyl carbon the lowest possible number.
Okay, let's actually see this in action. Take a look at the aldehyde up top. Right away, we know that carbonyl carbon is number 1, period. Then we count the main chain. It's 7 carbons long, so the base name is heptanal.
Now we just have to find the other stuff attached, the substituents. We've got a bromo group on carbon 4 and a methyl group on carbon 3. We list those alphabetically, so the full name is 4-bromo-3-methyl-heptanal. Got it? Now let's look at the ketone down below. The main chain has 5 carbons, so it's a pentanone. Now we have to number it to give the carbonyl the lowest number. In this case, it's on carbon 3 no matter which way you count from. Then we find our methyl groups at positions 2 and 4. So the full name becomes 2,4-dimethylpentan-3,1. See how the logic works?
But wait, what about rings? You knew it was coming, right? They have their own special rules, but they're not too bad. When you have an aldehyde group just hanging off a ring, you name the ring, and then you just add the suffix carbaldehyde. So a cyclohexane ring with an aldehyde becomes cyclohexane carbaldehyde. Easy enough? Now, if the ketone is part of the ring itself, that carbonyl carbon automatically gets to be carbon number 1, and you just start counting around the ring from there.
And then we have the aromatic compounds, which are always a little bit special. The simplest one, that's a benzene ring with an aldehyde group attached. Its technical IUPAC name is benzene carbaldehyde. But honestly, its common name, benzaldehyde, is so widespread, so common, that IUPAC just threw up its hands and said, okay, fine, we accept it. So benzaldehyde is now the official base name, and other similar aromatic aldehydes are just named as if they're derivatives of that.
Okay, let's put this all together for a second. This table's a fantastic little reference, kind of like a cheat sheet. You can see the old-school common name right next to its modern logical IUPAC name. So, formaldehyde is really methanol. Acetaldehyde is ethanol, and acetone, as we saw, is propan-2,1. This really drives home the difference, right? You've got the historical names versus the superlogical, systematic IUPAC names.
So, what's the big takeaway from all this? Well, it's that by understanding just one simple structure, that carbonyl group, and a handful of logical rules, you can now decode the language for thousands upon thousands of molecules that literally shape our world. Everything from flavors to solvents. It's amazing how a simple pattern can lead to so much complexity. So now that you can read the carbonyl code, what other chemical stories are out there just waiting to be told?